Good morning, everyone. Thank you for choosing this session. My name is Geoff Bennett. I work for a company called Infinera. A couple of years ago, we actually acquired a metro optical company called Transmode, who are partners with Santa Monica Networks for many years. So that's kind of a bit of the history behind it. Also, Elisa is one of Infinera's European customers. So there's quite a bit of tie-up. And what I wanted to do today, this is not a product presentation, it's not a marketing pitch, it's actually a technology tutorial. And I think most of you will be techies. You know, this is the number one rule: know your audience. You're all geeks, you use the internet, you know that the internet's growing like crazy, so I don't need all of those slides that from the Cisco Visual Network Index that tell you it's growing like a weed. It is growing like a weed. There's huge amounts of information being moved around the world. And what I wanted to try and do is explain how some of that is moved over longer distances. What's the technology behind that? And the way I want to do it is through some science demonstrations. And if you've got kids, or looking at the age range, some of perhaps younger brothers or sisters who are looking for ideas for science projects at school, hopefully these experiments will give you an idea of what you could suggest to them. So I think one of the first questions, how do we carry all of this information that's moving around the internet? The thing is, most of us experience the internet through access technologies, things like wireless, cellular telephony and that kind of thing. Maybe copper if it's DSL connections into your home. It could be fiber into your neighborhood, into your building. And of course, something has to carry all of that information. Whatever that something is has to operate at much higher speeds and more capacity than those access technologies. And the technology of choice is a multi-wavelength or multi-color fiber technology. We call it DWDM. What it isn't, by the way, is satellites. A few years ago, my wife bought me a book from the 1970s. It was one of these kids' science books, and it said, one day everybody will have a computer, and those computers will talk to each other over satellite links. I want you to try to picture something in your minds. An Olympic-sized swimming pool. We're in the Olympic Hotel here, think about the size of an Olympic swimming pool, the amount of water in that swimming pool, and think of that as the volume of information that passes every second over the internet. The amount of that information that is passing over satellites is a bucket that you might dip into the swimming pool. That's the volume of data that goes over satellites. The rest of the swimming pool is passing over optical fiber. So that's how important optical fiber transmission technologies are in terms of internet communication. This is a kind of zoom in to that view. If we want to transmit information between continents, between countries, we pass over international links. These are subsea cables. They pass under the ocean. And it's a fascinating technology. The fibers are laid by massive, great fiber-laying ships. Every 50 kilometers on these cables, you have an amplifier. So it means that the optical cable doesn't just carry light, it has to carry electricity as well. Imagine the cable that runs across the Atlantic Ocean or under the Atlantic Ocean. At each end of the link, one end you have plus 6,000 volts, at the other end you have minus 6,000 volts, and the sea itself is acting as the earth. And this is how you power the amplifiers that are along that cable. Then we dip into pan-continental networks across North America, across Europe, and I live in the UK. Virgin Media is one of our biggest customers in the UK. They have a national fibre backbone. And then we drop down into neighbourhood fibre, and it goes down and down and down in terms of the hierarchy. Now, light is a really good way to communicate because you can carry an enormous amount of information on light. It will go incredible distances, and of course nothing travels faster than light. It's the universal speed limit, if you like. So how fast does light travel? Well, now we're all digging up our high school physics, and we think, yeah, there's a 3 in it, right? Yeah, it's 300,000 kilometers per second. And you see I have a little asterisk there because that's the speed of light in a vacuum, or in air. It's almost the same, actually. It's not the speed of light in optical fiber. Optical fiber light travels about 2/3 of that speed, 200,000 kilometers per second. Depending on the transparent medium, light will travel at different speeds, but this is the universal maximum. You can't go faster than a vacuum. If you happen to be in a physics department somewhere and you get a result where light is traveling faster than this, you've made a mistake. Okay, there were some Italian scientists a few years ago who thought they'd sent neutrinos faster than the speed of light. Oops, yeah, they've forgotten some cable measurements. But it's proven true over and over again that this is the universal speed limit. Now, to see light travel, because it travels so quickly, really we've got two different options. One is that we can slow down time. And this is an option that's only become available recently. This is a video from the MIT Media Lab, and it shows a beam of light actually passing through that bottle. And that's a trillionth of a second exposure time. It's a little bit tricky to do that. You can't do that on your phone camera. It needs slightly more elaborate equipment, and it also needs incredibly bright light. So the other option that we have is we can use very long distances. And in fact, the first people who really figured out that light doesn't just move instantaneously were astronomers. It's Galileo, Kepler, people like that, who were looking into the night sky over very, very long distances. And to give you an idea, we are here on Earth, and the moon is over there, and it's 370,000 kilometers from the Earth on average. It moves in and out a little bit, and that's 1.3 light seconds. So I built a PowerPoint animation that is a scale animation of how quick a beam of light would actually take to get to the moon. And of course, we know the Apollo astronauts in 1969 actually left mirrors on the moon's surface, so now astronomers can check the distance between the Earth and the moon to centimeter accuracy over those distances because they can bounce a beam of light off the moon and back. So light travels very quickly. It seems like a very good way to communicate, but we need a great source of light. Now, communicating with light isn't all that new. The ancient Greeks and Persians polished their swords or their shields, and they used light flashed off the sun. So this heliograph communication has been used for a long time, but look outside. It wouldn't work all that well today, would it? I live in the UK. How many days in the year does the sun actually shine in the UK? What we need is a reliable source of light. You could use a torch, and people do. Secret agents flash messages at night. We've seen that on James Bond movies and so on. But really we need something different. We need something like a laser. This is a photograph of Theodore Maiman, who worked at Texas Instruments in the 1960s. That's his ruby laser. It's not particularly compact, but it's getting there. The interesting thing about a laser is that you have certain properties. You have very intense light. It's a single color. It's monochromatic, and it's coherent. Now, that's a technical term. I'm going to use that term later in the presentation, but just park that thought for the moment. All lasers share those properties. But if you build a laser, instead of it being a big desktop kind of laser, if you want something small, you move to a semiconductor laser. So semiconductor lasers are very small. This is how small they are. This is the eye of a needle, and this is the semiconductor laser chip. So it's very, very small. The other thing about a semiconductor laser, it's very efficient in converting electricity into light. It can also be mass-produced, and they're incredibly reliable when you produce them. There's no moving parts. It's a solid-state device. Like a lot of the electronics that we use today, it's incredibly reliable. So semiconductor lasers are the kind of laser that we use in telecommunication systems. We don't use other kinds of lasers. Other kinds of lasers are used for cutting metal. They're used for different purposes. Americans are trying to shoot missiles out of the sky with lasers, but not semiconductor lasers. This is what we use for communicating. And we need the right kind of semiconductor. Many of you in this room today will be very familiar with silicon as a semiconductor material. It's a fantastically successful electronic semiconductor. It's also really good for optical uses, but for passive devices, it's the wrong kind of semiconductor to use for lasers. and there's nothing we can do about it. When the universe was created, when the laws of physics were formed at the Big Bang, silicon became an indirect bandgap semiconductor. You can't change that, and you can't make lasers from indirect bandgap semiconductors. There are direct bandgap semiconductors like gallium arsenide and indium phosphide, and those are the kinds of semiconductors we use for lasers. Now, when you build a laser, you can actually choose the color of light that you want to transmit. And in fact, this is the electromagnetic spectrum. These are very energetic rays at this end, gamma rays. They're formed in the heart of an exploding star. It's pretty intense. And then at the other end of the spectrum, we have long radio waves, such as we pick up from the echoes of the Big Bang. The background, microwave background radiation would be examples of that. So these are two cosmic phenomena that operate at the extreme ends of the electromagnetic spectrum. As we move across this, X-rays, ultraviolet, infrared, microwave, radio waves, and so on. And then somewhere in the middle, we have these weird colored waves, and that's a special part of the spectrum that we call the visible spectrum, because our eyes are sensitive to those different wavelengths. Most people, on average, can see somewhere around 390 nanometers up to 700 nanometers. 390 nanometers, that's a very short wavelength, we'd call sort of purple colors, and then 700 are red colors. All the other colors of the spectrum sit along that continuum. Now, interestingly, I have some laser pointers that I sometimes use. The problem with a laser pointer is there's no such thing as a safe laser. So in public demonstrations, I can't really bring these lasers, but if I could have shown you that there is a 405 nanometer laser that's sort of a bluey purple color. There's a 532 nanometer that's green, and then a 650 nanometer that's red. And you can buy these on eBay for a few dollars, $4 or $5. They're just simple laser pointers. The green one is the most useful for two reasons. It's very bright, and that particular cheap laser that you get from China is very bright. And the other thing is our eyes have evolved to be very sensitive to green radiation. If you want to know why, I can't remember the name of the movie actually, but basically it's predators. As we evolved, we evolved in a kind of jungle environment, and the ability to see different shades of green became a very useful evolutionary trait. Whether you're a hunter or whether you're the prey, it's very useful to see movement in the jungle. So our eyes are particularly sensitive to green radiation. Interestingly, we don't use any of those wavelengths for communication, because it turns out that in optical fiber, which is made of glass, these wavelengths tend to be absorbed. Now, it doesn't matter very much for a sheet of glass that's in a window, because it's extremely thin. But when you're transmitting through hundreds or thousands of kilometers of glass, it starts to become very important if this energy is absorbed by something in the glass. So we use infrared radiation. We use infrared wavelengths, particularly 1550 nanometers, which is right in the middle of something we call the C band or conventional band for telecommunications. Now, we can't see infrared radiation, but here's your first little science experiment. So when you get home, you find your TV remote, and you point it at your eyes, and you press a button, and you won't be able to see anything. There'll be a little LED on the front of it, and you won't be able to see anything coming out of it. So what you then do, you get your phone, and you do this. So I actually made a video of this to make it easier. So this is a remote control. Now, you just push the button, and you can see it. And that was a high-end digital SLR. Most cell phones will do this. If you have an iPhone, it won't work. You won't see it. Apple, for some reason, puts in a filter that blocks those infrared rays, but it's Apple. Doesn't have to make sense. Now, those simple laser pointers, I said there's no such thing as a safe laser. They're not very dangerous, honestly, but you need supervision. You need adult supervision. Clearly, I am not qualified for that. But if you're doing this with your kids, you can make sure it's safe. Just don't have them pointed towards their face. Now, if I could have brought a proper laser, and it doesn't have to be all that dangerous, right? I'm talking about a Blu-ray recorder laser. In other words, the laser that actually writes to the Blu-ray disc. If you've got lots of time on your hands, you could do something like this. Blow up 100 black balloons, and you put them against a Blu-ray laser that you can get out of an ordinary Blu-ray recorder. And you just turn it on, and that's what happens. Now that is really cool, I think. But you know, I'm basically a kid. So the laser wins. Now, the interesting thing is, if you can generate that much optical power, why go to all the trouble of optical fiber? Why don't you just shine the signal through the air? That seems like a really good idea. Air is free, right? People, interestingly enough, as you know, governments actually regulate the electromagnetic spectrum for cell phones and those kinds of communication. They don't regulate optical wavelengths. That would be quite difficult because we have to pay to actually look at stuff. And there's no government people in the room. I don't want to give you any ideas, right, for additional taxation. But so why not send light through the air? Well, actually, there is an entire marketplace called free space optics. It's a real thing. You can buy this stuff. You can put them on the top of high buildings, and you can shine light between the buildings, and you can communicate at reasonably high data rates for reasonable distances, a kilometre maybe. You know, in climates like the Baltic area, the UK, it doesn't really work for this reason. This is a view from the London Eye. If any of you have been to London, this is one of the tourist attractions, and that's your typical view from the London Eye on an average day in London. Now, as you can imagine, the problem is there's a lot of stuff in the atmosphere. Now, in that case, stuff is water vapor. But we also, even on clear days, you have pollen, you have dust particles that will scatter radiation. In other words, the photon is minding its own business, it's traveling through the air, and suddenly it hits a pollen particle and it'll bounce off. That's scattering. And of course, you are reducing the strength of your signal. For every photon that's scattered away, it's not going to get to the receiver, which is a bad thing. Now, again, here's an idea for a science project. You can explain a lot of natural phenomena if you understand scattering. You can see the consequences. For example, if sunlight is white, why is space black? Why is the sun, why does it look yellow when it's high in the sky? Why does it look red when it's at sunset? And why is the sky blue? You can explain all of these things if you understand scattering. Now, this is how you do it. There's an important piece of information. This is the vital piece of information. Shorter visible wavelengths are scattered preferentially. This is the key thing that you have to point out in a science project. So this end of the spectrum will tend to bounce off those dust particles or pollen particles preferentially, more than the red end. Now when that happens, you can imagine the sun is white. It's actually a white dwarf star. That's what astronomers call our sun. So that white light, which is a mixture of all these different wavelengths, they're trying to get to your eye. What happens, they encounter a pollen grain on the way, but the blue and the shorter wavelengths are actually scattered off. They become the blue glow, or the blue color in the sky, and the rest of it hits our eyes. Now, you know, you look up the reasons why the sky is blue. Some people say, oh, it's a reflection of the sea. Well, the sea in the UK is a kind of greeny brown. don't know about in the Baltic. I have been to places where the sea is blue, but not anywhere near here. So that's the key piece of information. That's why the sky is blue. And interestingly enough, you can draw this diagram as well, which tells you all the stuff. Imagine white light is coming from the sun. An astronaut out in space, there's no particles out in space to scatter the light. So you look around and they see a black space around them, other than sources of light. The sunlight looks white. There's been nothing scattered from it so far, but when it comes into the atmosphere, that shorter wavelength radiation is preferentially scattered. Somebody that's looking up at the noonday sun, don't look at the noonday sun, but if you kind of glance at it, you might notice that it looks a bit yellow. It's not white. And that's because these blue wavelengths have headed off somewhere else. And the sky now looks blue. Somebody in a different part of the Earth, there's more atmosphere for the radiation to pass through, so more of the blue radiation disappears, and what is left now looks orangey or red. And in fact, you may have heard of, I don't know if you have this proverb, red sky at night, sailor's delight. Have you heard, if anybody's heard that proverb? That actually has a scientific basis in truth. because in most of Europe, our weather systems come from the west. And if you are looking to the west and you see the sun, that's sunset, right? That's at night. So red sky at night means you're looking at dry air, because you're looking at air where there's a lot of scattering. And that means there's lots of dust and pollen. If the air was wet, it would be washed out of the air. So, so that means the weather system that's coming towards you is a dry weather system. So there's definitely some valid science in that proverb. So if we think about how we could demonstrate this, right? So if you're going to do a science project, you want a real demonstration. So I put together this video, and I have 3 vases. These happen to be plastic ones for safety. They're a few dollars on eBay. I've got a white torch, and I've got a glass. I actually ended up using a box to rest the torch on. That's just to get the torch up to the right level. What I'm doing now is putting some skimmed milk into the middle vase. I'm putting some atmosphere in there, because I haven't got miles and miles. I've only got a few centimeters. And what you do, you just put enough milk into each of them for the effect that you want. So no milk in this one, a little bit of milk in this one, a little bit more in that one. So this is the view of the torch through clear water. It's just a white torch. Again, if you're going to film this, by the way, you have to set the white balance on your camera so that it appears white, otherwise it will start to appear orange or yellow maybe. So now I'm going to move the first vase in the way, and you see now it looks yellow. And it's not because the milk is coloured yellow, it's because the milk is scattering the radiation. And sometimes, if you have enough faith, you see this as a sort of blue glow around here. And it's like it's the blue radiation from the white light is being scattered into the milk. And so once you've shown them that, you can move the next light in. This is the one with the most milk, and you see that now looks orange. And in fact, I should have gone back and fixed the focus on the camera, but I thought, no, that really looks like the sun, actually, when it's out of focus. But you can see there's an additional scattering there, and that's like a sunset. So simple experiment, nice and safe to do. Even if you didn't have scattering, free space optics has an obvious limitation. We live on a round planet. The Earth is round. Unless you're American, because a lot of Americans don't believe the Earth is round. There's a lot of experiments you can do to show that. When somebody walks across the horizon, they disappear that way. It's kind of indicating that the Earth is round. When a ship sails across the horizon. Anyway, because light travels in straight lines, you can only go so far before the light will, or your receiver disappears off the other side of the planet. So there's a natural limit for free space optics. So what we need to do is to be able to guide light, because light will naturally want to travel in straight lines. If we could guide light, we could deliberately choose a medium that wasn't full of stuff. It doesn't have pollen grains or water vapor or anything like that. It could be very transparent to light. And also, you could overcome the distances of the curvature of the Earth by guiding the light around that path. So what properties of light could we use to create this waveguide? So I've told you about scattering. This is the next property, and this is refraction. Now refraction is very simple to demonstrate. You can take a glass of water, you can stick something straight into it like a pencil, and you can see it appears to be bent. And refraction is the idea that as light moves from air into water, the speed of light changes. And the speed, I mentioned the speed of light in air is about 300,000 kilometers per second. In water, it's about 225,000 kilometers per second. And it causes us to see that the pencil is bent. And we say that light is refracted at that boundary. So refraction is an interesting thing. The refractive index is how we measure the speed of light in a given transparent medium. It's the ratio of the speed of light in a vacuum to the speed of light in that medium. And it should always be greater than 1. If you get a result where it's less than 1, you've made a mistake, go back and figure out what you did wrong. The refractive index should always be greater than 1. In a vacuum, it's 1 by definition. In air, it's a little bit higher. The speed of light in air is almost the same as the speed of light in a vacuum. In water, it's 1.33. In glass, it's 1.5. Oh, in diamond, it's 2.42. And again, a little piece of trivia, this is one of the reasons why diamonds sparkle. And in fact, when people try to make fake diamonds, they try to use a material that has a high refractive index. So cubic zirconium, which is the favored fake diamond material, has quite a high refractive index. So a couple of demonstrations that you can do on refraction, quite good fun for kids. And the first one, I'll call it the levitating coin. If you don't get it right, it becomes the disappearing coin, by the way. The levitating coin is slightly harder to do. I'll show you why. So for this, you need a glass, you need a coin. I've actually put a piece of paper here so you can see the coin more easily, and you just need some water. So you put the glass on top of the coin, and you can see the coin there. And then you take the water and just pour it into the glass, and you should see the coin disappears from the bottom and it reappears up here. Now that's the levitating coin. You need to get exactly the right amount of water in the glass to do that. If you just want to do the easy one, which is the disappearing coin, fill it up about halfway, half as much as that, and the coin won't appear. So that's quite a nice, cute trick. Nice and safe for kids. There's this one, the reversing arrow. So what you need here is a piece of paper with two arrows that are pointing in opposite directions. You need a cylindrical vase. You have to have a cylindrical vase. And you need some water here to pour into the vase. And you pour up to the level between the two arrows. And watch what happens. The arrows are now pointing in the same direction, because that vase is now behaving as a convex lens. So it's, again, nice simple demonstration of how refraction works. So all of this is building up to the point where we now have the kind of techniques we need to create optical fiber. And optical fiber is very, very interesting. If you've seen optical fibers, you may have seen something like this. It's a cable, obviously. Inside the cable there are these fibers. And it's interesting to realize how thin a fiber actually is. Because here, this glowing filament here is the optical fiber, and that's a human hair. Right? That's how thin the optical fiber actually is. It's incredible that we get all of this bandwidth, all of this capacity over something that is so thin. Now, how do we tell people, particularly school kids, how optical fiber works? You notice I say tell people as opposed to how it actually works. So we tell them that it's about total internal reflection. And because it's very easy to demonstrate total internal reflection. If next time you go to the swimming pool, hold your breath, go under the water, and you look up at the surface of the water, and you'll see that it acts like a mirror. You'll be able to see the bottom of the pool and other people's legs usually in the swimming pool. This is a picture of somebody sticking their hand in some water and the reflection on the upper surface. So the way this is working is that the higher refractive index of water is trapping the light in because of refraction and total internal reflection at the boundary. Optical fiber is built in layers. You have a core, you have a cladding, and then a buffer. Buffer is usually a plastic coating that you put on the outside, but these are two different kinds of glass, the core and the cladding. And the cladding is made of pure silica, pure glass, silicon oxide. But you put a small amount of germanium oxide into the core to raise the refractive index. It raises it by about 1%. And the effect of that is that there becomes a refractive index boundary. If you look along the horizontal section through the fiber, when the light tries to escape, it bounces off that boundary and it's trapped within the fiber. Now, if that's how fiber really worked, the signal would go about 100 meters, right? That's not how it really works. Very old fiber types, multi-mode fibers, did work that way, kind of worked that way, but not really. And so we can actually demonstrate this fairly easily. If you find a perspex block or a glass block, if you have one, but obviously if you're thinking about experiments for kids, don't use glass. Right? All it takes is they drop the glass, it shatters, and now you've got a dangerous situation on your hands. Try to find stuff that's plastic, basically. So a perspex block and a green laser pointer. And I use my 5-year service award at Infinera for this. And this is one of the laser pointers I would have brought along if people didn't regard it as a safety violation. So what I'm going to do is just shine the laser through it, and that's like it traveling along the fiber. So now the beam tries to escape from the fiber, and as soon as it tries to get to the edge of the fiber, you can see it bounces off. And it is trapped within the block, and it will be trapped within the fiber. So it's a very easy effect to demonstrate that. So that's typically why we tell kids it's how it works. If I had a lot of time and patience, I could do what this chap on YouTube does. So what he got was like a rectangular fish tank. And first of all, he put some water into it, clean, ordinary, pure water. So then this jug, it's about a 1 litre jug, and he takes a kilogram of sugar and dissolves a kilogram of sugar in that litre of water. And you can see he's using a card there, so he's gently pouring it onto the surface of the water. So what happens, the two things about that sugar solution: first of all, it's denser than water, so it starts to sink through the water. And secondly, it has a higher refractive index than the water. Now, after about 2 hours, once it's equilibrated, you can do this. You can actually see the light bending. It goes through a curved path, and it's going through a gradient of refractive index as the syrup is falling through the less dense water. That's the actual path of the beam. That's the straight line path, and so you've got a lower refractive index and higher refractive index portion of the liquid. Again, you know, that takes hours, and sometimes it doesn't work, but there's a YouTube link there if you want to watch it. Now, a quick reminder of what we've spoken about so far. Light wants to travel in straight lines. If we send light through the atmosphere, it will be absorbed or scattered by impurities in the air. The Earth is curved, so there is a natural limit to free space optics. And what we need to do is use refraction and the properties of glass to create this optical waveguide. That's what optical fiber is. That's the key point about optical fiber, that it is a waveguide. So, now that we've achieved that, we need to move to the next step, which is how do we put the ones and zeros onto the light? That's called modulation. And a simple example of modulation would be a signaling lamp. And I found this YouTube video of a chap who rebuilt a Navy signal lamp. And you can see this has got a lot of properties of real communication. Notice that the light, the bulb, is on all the time. We don't turn the bulb on and off. We use the shutter to allow the light to be seen or not seen. And that's important because in real communication systems, you have the two choices. You can take a laser and you can directly turn it on and off. That's called direct modulation. Now, you can do that up to low data rates, maybe a gigabit per second, and it will work. And it'll be cheaper to do that. But the problem is, when you turn the laser on, there's a thermal spike, and that actually makes the wavelength of the laser wobble. And if you're trying to do wavelength division multiplexing with lots of channels that are closely spaced together, the last thing you want is the channels to be wobbling like that. So you don't use direct modulation when you have lots of wavelengths on a fiber. You use indirect modulation, or you have an external modulator, which is where you put a shutter in front of the laser. So there are those two modes of operation. Now, for the first 30 years of optical transmission, it was pretty much as simple as that. You put something in the way, you take it out. If there's light, that's a 1. If there's no light, that's a 0. Right? It's kind of Morse code. And it worked perfectly well. It's called on-off keying. Sometimes people call it non-return to zero modulation. And this is what it looks like. You know, if you have some light, it's a 1. No light, it's 0. Light, that we have 1s. And it means you can build a very, very simple transmitter circuit. You have a chip that's a laser, and you have another chip that is a modulator, the shutter. And when that passes through many kilometers of fiber, you have a receiver circuit at the other end. And the receiver can be very simple. It's a photodetector. And really, it's nothing more than a solar cell. You know, when light falls onto a solar cell, it generates electricity. That's what happens with a photodetector. When the light falls onto it, it generates a pulse of electricity, which you can then take into an electrical circuit and process it. So If the way that you modulate the light looks very digital, it looks like ones and zeros optically, it's going to look like ones and zeros electrically as well. So you can have a very, very simple circuit. And this will work for data rates up to about 10 gigabits per second. There's a problem with that kind of receiver, though, that has limited advances in communications for a long time. This is we call it a square law detector. In other words, the response of the detector is not linear to the amount of light that falls onto it. Now that's got a very, very important consequence that I'll tell you about in a moment. But for a long time it just didn't matter. So this was okay for up to 10 gigabits per second per wavelength, and some of you who have followed our industry will know that around about the year 2000, 10 gigabits started to become quite popular, and it remained the most popular long-distance wavelength for the next 10 years. And for all of these reasons, that's why we kind of stuck at 10 gigs. It became a sticky technology, because it was kind of difficult to go beyond 10 gigabits. You have to change lots of different parts of the technology to break that 10 gigabit barrier. So the thing is that things started to get very, very difficult as we transmit faster than 10 gig. Now, one of the reasons for that is we need to consider, when we put bits onto a fiber, how long is the bit? If you had a length of fiber across this room, how long would a bit occupy? How much of that fiber would an individual bit occupy? So let's take a look. For fast Ethernet, 100 megabits per second, it would be about 2 meters long. For gigabit Ethernet, it would be about 20 centimeters. 10 gigabit Ethernet, 2 centimeters. For 100 gigabit Ethernet, it's 2 millimeters. And that's, I know 100 gigabit Ethernet, you actually use parallel channels, so it's not quite as easy as that. But you can see the point. The bit time is getting shorter and shorter. That's a 2 millimeter bit that's moving at the speed of light, right? That's fairly challenging from an electrical circuit point of view. Now, I'd like to explain, there's a whole set of optical impairments in fiber. And again, I don't want to get too bogged down in technical things. I wanted to choose one of them, which is chromatic dispersion, and I'd like to just explain it in some detail, because chromatic dispersion is a fairly easy one to understand. Chromatic just means color, right? I think it's the Greek for color, chromos. And dispersion means spread. And so chromatic dispersion is where the signal spreads out because of color. Now, again, remember with scattering, a key point was that the shorter wavelengths were scattered preferentially. Well, with chromatic dispersion, the key point is that longer wavelengths travel at faster speeds than shorter wavelengths through fiber. That's if you have a material that has something called normal dispersion. Most materials work that way. If you have anomalous dispersion, it's actually the other way around. But there's very few materials that works in. This is why it's important. When we send a signal, like a 1 or a 0, you can imagine that as a pulse of information. And hopefully that pulse of information, because you're transmitting with a laser, it should be one color. Yeah, it's never quite that simple. At the precision that we are talking about, it's not one color. If it was one color, what would happen is that nice digital square pulse would travel down the fiber, and at the other end, you could very easily interpret whether that's a 1 or a 0. You'd have a really high probability of making the right choice. So, unfortunately, when we modulate a signal, you don't have a monochromatic laser anymore. It spreads out a little bit, only a very small amount. The precision that we're talking about, it's important. So when this is not 3 pulses, this is 1 pulse. It's just the different color parts of the pulse. So this is a longer wavelength because it's red, this is a shorter wavelength because it's blue, and the green is somewhere in between. So when this single pulse travels down the fiber, the components, the different color components, spread out. And that's called chromatic dispersion. So now you've got a much wider spread than it started along the fiber. And the further you go, the worse it gets. Chromatic dispersion is an example of a linear impairment, because if you went twice as far down the fiber, it will be twice as bad. That's a linear impairment. So instead of it being a nice square pulse, it tends to spread out like that, and there'll be the red end of the signal will arrive first, and the blue end of the signal will arrive afterwards. Dispersion gets worse as you increase the transmission rate as well, because if you transmit at a slow rate, there's plenty of space between the pulses, so if they were to spread out, you've still got a good chance to figure out whether that's a 1 or a 0. But if you increase the transmission rate and move them closer together, the spreading is exactly the same as you travel down the same distance of fiber. So they now start to overlap, and it's very, very difficult to make out whether that's a 1 or a 0. The reason I've chosen chromatic dispersion out of all the different impairments I could have talked about is that for the whole era of 10 gigabit per second transmission, chromatic dispersion was our enemy. It was probably our worst enemy, really. And all sorts of techniques were developed to try to compensate for chromatic dispersion. And suddenly, things changed. In 2010, things changed. Because what we need to think about is, can we send more than one color down the fiber to increase the amount of capacity that we can transmit? And if we can, why don't the multiple colors get scrambled up? And the other question I'm going to be answering is, how do we break that 10 gigabit per second barrier and transmit faster? So let's go back to this idea of laser light. I told you that it was monochromatic, and of course I lied. It's not monochromatic at the level of precision that we're talking about. But also, the important point is, if you're sending these different colors down the fiber, as long as their wavelengths don't overlap, you should be able to distinguish the energy of one signal from the energy of the other signal. And that means you could send multiple signals down the fiber, they don't get mixed up. There's a problem, because that's how a laser looks when you just shine light continuously. But when you start to put 1s and 0s onto the laser, when you modulate the laser, it starts to spread out. And the higher the rate that you modulate, the more it spreads out. And at some point, they are going to start to overlap. And that's when you get cross-channel interference, which is bad. It's now going to start to impact how far you can go or how fast you can transmit. So how do we get these multiple wavelengths onto the fiber in the first place? And then once we've got them there, at the other end, how do we separate them? Well, it's time to say hello again to our friend refraction. Refraction was the thing that helped us to build a waveguide in the first place, but refraction is also how we're going to manage these wavelengths. So it's the basis of dense wavelength division multiplexing. So again, that's a technical term, so let's just decode it. Multiplexing means sharing. You're sharing a higher capacity channel between lower capacity signals. Wavelength division just means I will be using wavelength as the way to multiplex, as the way to differentiate one signal from another. And dense just means I'm going to try to pack these wavelengths, these different channels, as close together as I can to get more capacity on the fiber. That's all it means, right? So, sharing a single fiber using multiple colors of light, we can go right back to Isaac Newton in the 1600s. Now, Isaac Newton was an interesting guy, mad as a hatter, and he was an alchemist. He was an incredible scientist of his day. And one of his theories was in optics. And he's very famous for an experiment where he took white sunlight, he passed it through a triangular glass prism, and the light split into different colors. Now, that's in the 1600s. So, lots of people had observed this effect. As soon as you start making glass windows, these were very imperfect structures. They had wobbly glass, and it was very common to have these rainbow effects. If you live somewhere where the sun actually shines, right? You could see these rainbows in your lounge and so on. And I don't think they called them lounges in those days. But anyway, the key point that Isaac Newton made, a lot of people were wrapped up with religion back in those days. And the philosophy was that white light comes from heaven, and therefore it must be pure. And when you pass white light through a prism, you are adding the colours to it. You are adding the impurities to it. Whereas Isaac Newton said, actually, I think the white light is a mixture of light, and the prism is separating it. And everyone said, no, that's nonsense, that's heresy. And the way that he demonstrated it, nobody actually draws this diagram, but he used two prisms. So the first prism separates the light into different colours. And then what he did was put a second prism on the red light, let's say, and he showed that when you put one colour through a prism, you get one colour. You don't get the white light back. It doesn't add the impurities back. You still get the red light because there's nothing to separate them. So that's how he proved his theory that white light was actually a mixture of light and the prism was separating it. Very clever. If you're a Pink Floyd fan, you'll have seen this as well. So now the idea here is that you're trying to send these different colours onto the same path. So what you do is you shine your transmitters in at different angles to the prism, and the light ends up coming out the same path. That's how you get the light onto the fibre. And then at the other end, key piece of information for you. When you have a receiver, see, the laser is one colour, and it will shine with one colour-ish. But when you get down the other end, a receiver will receive any colour. So if you shine the red light onto what you think is the blue receiver has no idea that that's red light. It's just seeing light. It's a wideband receiver. So what you have to do is put a separator before the receivers, because the receivers will receive anything. So in order not to get a mixture of signals on the receiver, you have to separate it first. And again, you just use a prism. We don't call them that because we want to charge lots of money for them, obviously. So we make some fancy name up, but they are basically prisms. Now this is how fibre capacity can be scaled up. If you imagine that the total capacity that you get on a pair of fibres, and remember, fibre is quite an expensive thing. It's not necessarily just the cost of the fibre, it's how much it costs to lay it. You've got to dig up the ground, you've got to have expensive conduits and so on. It costs a lot of money to lay fibre, so you want to get the maximum capacity you can from it. So what you do, of course, you can have a data rate for each wavelength. Remember, we were at 10 gigabits per second for many years. But you can also increase the number of wavelengths on the fibre. So the total capacity becomes the multiplier of the two. And that's really important because as technology advances, sometimes it's easier to scale the data rate. You can move to a higher data rate. But sometimes it's just easier to put more wavelengths on the fibre. And having the flexibility to do both is extremely useful when you're trying to optimize the capacity at a given period in history. So how do we push the limits? Now, remember earlier on I said as these bits get shorter, the fibre impairments become more serious. As we modulate faster, the signals get broader, and these two phenomena interact. Because if the signal gets broader, then it's going to get this chromatic dispersion will become worse. So it's almost like nature and the properties of the fibre are trying to stop us transmitting faster. And that's why for many years, for that whole 10-year period, where 10 gigabits per second was the optimum data rate, chromatic dispersion was our primary enemy, because it was so fundamentally against the idea of us transmitting faster. Luckily, there are very clever people around. So what happens as we get to the higher data rates, we can ask ourselves the question, is there a better way to put the ones and zeros on the light than just simple on and off? And the answer is yes, we can use something called phase modulation. Can we build a smarter receiver than a direct detector? Now that direct detector is just that solar cell, that photo cell that says, oh yeah, that's a 1 or that's a 0. Is there a more intelligent receiver? Yes, we can use something called coherent detection, and we can apply signal processing to coherent detectors for reasons that I'll explain. Now, coherent, I used that word right at the beginning when I was talking about lasers. I asked you to sort of park the question, what does coherent mean? All it means is related to phase. So phase is the idea. When you have an optical wave, it has peaks and troughs, and you can see that these two waves, the peaks don't line up. They don't line up. And that means they're out of phase. They're not coherent. So you can have an example of that. Again, science project. You get a bowl of water and you just have drops that are dropping in there, and you make some nice ring-shaped waves here, and you can see where these waves overlap. Stuff happens. It's called interference. And it's because the height of one wave and the height of another wave, if they line up, the wave gets higher. If they're out of phase, they cancel out and the wave gets lower. So you can see what we call constructive or destructive interference patterns in pools of water. We can put the waves in phase just by shifting them so that their peaks line up, and at that point they'd reinforce. Let's give a real-world example of phase that you might find quite amusing. You get a toilet roll, and unfortunately, there's only a few ladies in this room. You will realize that men don't know how to do this, right? So what we see sometimes with two-ply toilet roll is that they get out of phase. And the way you get them back into phase, this guy's about to demonstrate, he takes the outer sheet, he just wraps it back around the toilet roll, and he tears off the excess. And now the two sheets are in phase again. If you can, there he goes. He's demonstrating that in phase now. So you could imagine, if you could do this with beams of light, if the sheets of toilet roll are the same, that's a 0. But now he's going to unwind them again, and he's encoding a 1 onto that toilet roll. So if you can do that with toilet roll, you can do it with beams of light. Now, how do we do this? This is called coherent transmission. So light is a wave, and waves have speed, wavelength, and frequency. The wavelength is the distance between the peaks, or between the troughs. And you can encode these 1s and 0s. Instead of using just on-off keying, as we did before, you can encode the 1s and 0s as phase changes, like with the toilet roll. Now, phase modulation is more tolerant to fiber impairments generally than on-off keying. That's a basic advantage. But much more important is that at the other end, when you detect the signal, coherent detection allows for very, very low noise amplification of the signal. And I'll explain how that happens in a moment. But here's the key thing. Let's go back. A coherent detector is linear. Remember I said the old photodetector was a square law detector. Coherent detectors are linear. Once you have a linear detector, you can apply digital signal processing to compensate for linear impairments. And chromatic dispersion is our big enemy, which is a linear impairment. There's also something called polarization mode dispersion, or PMD. That's also linear. Once you can apply that signal processing, the whole electronics world is open to you. Without that linear detector, it's very, very difficult to apply signal processing. But as soon as you have a linear detector, you can use powerful electronics. Let's explain how that really works with a coherent system. So here's a signal that has lots of interference patterns on it, and it's also here a mixture of wavelengths. Now, again, if you want to apply this as a little science project experiment, you can point out that many of you today will have already used a coherent detector. Because if you've listened to an FM radio station on the way in here, that is a coherent detector. Because what happens with radio, all around us are dozens of radio stations. How does that receiver in your car or on your phone, how does it tune in to just the station that it wants to receive? Well, we use something called a local oscillator to do that. And in a radio circuit, you have a piece of electronics that creates that reference frequency. In an optical coherent detector, you use a laser. That local oscillator is a laser in the receiver. And so here, for example, you can tune that laser to the wavelength that you would like to receive. And it also acts as a low noise amplifier. When that wavelength comes in, it's mixed with the local oscillator wavelength, and it boosts it. And because it's the same wavelength, it's really low noise. So it allows you then to pass that low noise signal onto the clever stuff. Now, let's hold that thought for a moment on what that clever stuff is, because I'd just like to tell you a little bit more about this. We now have a tunable detector, because if you change the wavelength of the local oscillator, you've now tuned into a different radio station, a different wavelength on the fiber. Typically, that's not how we use coherent detectors, because if you remember, there was a prism in front of this, and the prism just sends one color of light to the coherent detector. But there are people who are investigating ways that you could use tunable coherent detectors to lock into mixed wavelength signals. Those of you who have looked at switch architectures may be aware of a broadcast and select switch architecture. So it's where you broadcast all of the information that you want to send to every port on the system. You just broadcast that to everybody, and the receivers just tune in to the signal they want to receive. This would be a broadcast and select option for optical systems. So, how can a coherent detector be more sensitive to these higher data rate signals than a direct detector? What you're getting is a very, very complicated circuit versus the old simple circuit. But there must be a reason why that complexity is useful. So we can actually demonstrate it. And again, this is a nice little science experiment that you can do. So what we're going to do here is we're all going to turn our ears into coherent detectors. And you are going to listen to two notes. All I want you to decide is which of the notes is higher in pitch than the other. Is it the first note that's higher? Is it the second note that's higher? So here we go. This is the first note. Second note. So who thinks that note A was higher in pitch than note B? Nobody. Who thinks they were the same? Who thinks that note B was higher than note A? Everyone. Yeah, that's good. Because there's quite a bit of difference between these two notes. The first was 1,000 hertz, the second is 1,100. That's quite a big difference. I'm glad you were able to tell it. So, let's try again, make it a little bit more different. Here's note A. Note B. Who thinks note A was higher? For 4, 5 maybe. Who thinks they were the same? Who thinks note B was higher? Okay. Well, actually, note A was still 1,000 hertz, note B was 1,010 hertz, so obviously a lot closer together. But so now, the human ear is not that great at direct detection, because that's what a direct detector does. It's trying to directly decide, is that a 1 or a 0? Is that higher or lower? Was that an optical pulse, or was it just a little bit of noise that I saw on the line? Let's try a third one. Note A. Note B. Are they the same? Who thinks they weren't the same? So do you think, which was higher, note A or B? A was higher. Note B was higher by 1 hertz. Now obviously when it gets down to 1 hertz difference, we're really struggling. Let's make it a little bit easier. Instead of being direct detectors, let's use note A as our local oscillator and note B as our signal. So listen to them again together. See that beat frequency? Every second you can hear a beat frequency because there's a 1 hertz difference between the two. And that's how a coherent detector works. It can detect these tiny differences between the signal, not by trying to compare them separately, but by mixing the two and then making a comparison. Now, let's do remember number 2 was 10 beats apart, so this is what beat frequencies sound like at 10 hertz difference. That's a 10 hertz beat frequency. Now, some of you in the room might be familiar with radio technologies, and this is not a radical new phenomenon. It's new to the optical world. Well, new. 2010 thereabouts, we started to use coherent in commercial systems. Coherent, by the way, had even been used in optics back in the late or mid to late 1980s. There was a there was an initiative to develop coherent detectors for single wavelength optical transmission as very low noise amplifiers. And the thing that stopped that development was something called the EDFA. The erbium doped fiber amplifier was invented. It's a very low noise amplifier for multi-wavelength systems. There was no point at that time in having coherent detectors because we didn't have the digital signal processors to go with them. The two elements are like left and right hand gloves, right? You have to have them both. On a cold Estonian winter's morning, you don't want one glove, right? You want two gloves, okay? Oh, actually, there's a higher frequency. That's 10,000 hertz, I think. If you need those two gloves, if you need the left and right gloves, the optical circuit is the phase modulation type of circuit. What does the electronics actually do? What does that clever stuff do? Because it's just as important. So coherent detectors are linear. I mentioned that was a really important aspect. So now that we've got a linear detector, we can activate this clever stuff. The first part of it is very familiar to us. It's just a photodetector because we have to convert light into electricity. All of the processing that we do anywhere in our industry is all electrical. Nobody does optical processing. It doesn't exist. You do processing in electronics. So then you take those analog electrons and you digitize them through an analog to digital converter. You now have a digital signal that you can process in a DSP, a digital signal processor. And that can deal with any amount of chromatic dispersion. And it can deal with any amount of another kind of dispersion. It's called polarization mode dispersion. An amazing thing happened at that point. I only told you about chromatic dispersion. There's a whole set of nasty stuff that happens in optical fiber called non-linear impairments. And it turns out, if you can transmit signals through an optical fiber that has very, very high chromatic dispersion, you can minimize the number of the impact of non-linear impairments. It's just something that happens. We could never do it in the 10 gig world because chromatic dispersion was our enemy. Now we can do it because we can deal with chromatic dispersion. And suddenly, from our enemy, it becomes our friend. And it helps us deal with the next level of impairments, which are the non-linear impairments. It was a major breakthrough. And so we can end up with these very reliable high data rate signals. Now, how does digital dispersion compensation work? Now, I could put a whole bunch of equations on the PowerPoint slide and you'd all leave, right? Because they're very boring. Nobody really understands them. I certainly don't. So I'll try to show you a demonstration that I would love to do because this is so cool, this demonstration. But it really requires some complicated equipment. Let me explain what you're seeing here. In this, what we're seeing here are two concentric plastic cylinders. There's this inner cylinder, and you can see that there's a crank handle on the inner cylinder. So the inner cylinder will turn around. There's an outer cylinder, and the gap between the inner and outer cylinders has got a liquid in it. It's called glycerin. You can buy it from the pharmacy. It's actually used in medicines. In cough syrup, glycerin is what makes the cough syrup thick. And you can get pure glycerin, and it's just transparent. And you can see also the glycerin has the same refractive index as the perspex. That's why the inner cylinder is invisible. It's disappeared because it's got the same refractive index as the liquid surrounding it. So what's going to happen now is this chap is going to put 3 coloured blobs into the glycerin. Now the colour is irrelevant, it's just to show you how they'll mix up. And once he's put the blobs in, he's going to turn the handle 5 times clockwise. And that's like the optical signal moving down the fibre and being dispersed. You can see that it's getting all smeared out. Well, now he's going to start turning it anti-clockwise. I honestly promise you it's not reversing the film. And once he's turned it 5 times anti-clockwise, the 3 blobs come back. That's how dispersion compensation effectively works. As the signal travels down the fiber, it gets spread out by chromatic dispersion. And at the other end, through an algorithm, we reverse that effect. That's showing it in the analog world. Honestly, that's how we used to do it in the 10 gig world with something called dispersion compensating fiber. Back in the old days, what you had was the fiber that's laid in the ground, and that causes the dispersion to go in one direction. And in the service provider premises, you'd have rolls of dispersion compensating fiber, and they would reverse the effect of chromatic dispersion. They were expensive, they were quite high loss. We got rid of them when we moved to coherent transmission. They generally occupied about 10% of the fiber path as well, but they were just sitting in the building. They weren't giving you any more distance between two places. So that's how dispersion compensation sort of works. I think it's such a cool demonstration. So where are we going with all of this? We've been able to put more and more capacity across an optical fiber, there are limits, by the way. Back in the late 1940s, a guy that was working at Bell Labs in the United States, he was working on the very early aspects of communication theory. He was a guy called Claude Shannon. And when you read about optical transmission, very often now you'll hear about something called the Shannon Limit, and in particular the nonlinear Shannon Limit. So there is actually a limit to how much data we can put across optical fiber. But what we've been doing in the industry is pushing that limit further and further out through incredibly clever advances. So what we're seeing is this vertical scale here. This is the number of terabits per second over time. And I'm very, very confident that when we get to about 2020, there will be commercial technologies deployed. So not science experiments, not stuff that happens in a lab, not pilot experiments, but actual production equipment capable of 60 terabits per second with 1,000 kilometers reach on a pair of fibers. We're very, very close to that point even today. So we've come a long way in this last hour or so, and thank you for all staying awake. I'll just summarize a little bit of what we've learned. So I think of optical fiber as the asset that keeps on giving, because one of the astonishing things is that optical fiber started to be laid on a large scale in the mid-1980s. And at that time, you could get one TV channel, the equivalent of, across an optical fiber. Today, you could get 3, 4, 5 million high-definition TV channels across a pair of optical fibers quite easily. Millions of times more capacity, but it's the same fiber. You could go back to that same fiber that was installed in the 1980s and run today's coherent system. Turns out that's actually really good fiber for transmitting coherent signals over. Now it might be a bit dirty, you might need to clean it up a bit, but the ends particularly and any splices, you need to make sure they're not too high loss. But the type of fiber in the ground is perfect for coherent transmission. It's very important that we can use fiber as a waveguide as opposed to broadcast transmission like cell towers or free space optics, which have limits on how much information you can transmit. We use refraction to make fiber and WDM work, and coherent transmission and detection is what allowed us to break that 10 gig barrier. What does a 100 gig coherent optical circuit actually look like in terms of the components? And this is kind of what we make. So, of course, we have to have a laser. We have to have modulators that put the ones and zeros onto the signal. And because it's an optical circuit, you don't use wire. You don't use copper wire to join these together. You use little pieces of fiber. And one of the problems when you ship this equipment around the world, that fiber breaks. And so those fibers are a big source of dead-on-arrival failure for a lot of optical equipment around the world. So then you send that signal through many kilometers of optical fiber, and you have a receiver at the other end. You have demodulators that separate all of those phase changes. You have your local oscillator laser, because it's a coherent system. You've got lots of photodetectors and lots of connecting fibers that join the circuit together. But we're talking about multi-wavelength operation. What's the point in building a single circuit? That's not scaling anything, is it? What you really need is to be able to take multiple optical circuits. All of the components for those multiple optical circuits and also additional components that are going to combine those wavelengths together and separate them at the other end, the prisms that I was talking about, that combine and separate wavelengths. What Infinera does, and we're the only company in the world to do it, is we take all of that and we put them onto 2 chips. One for transmit, one for receive. We integrate 600 optical functions onto those chips, but we eliminate over 250 fiber connectors that you would have needed between discrete optical components. And when you do that, you end up with incredibly high density, low power consumption, and very high reliability. You can also do architectural re-engineering, and if you want to come and discuss that at our booth, we'll be happy to do that, because it offers major changes in the way that service providers can build optical networks. So, we put those things in, we don't sell them to anybody else, by the way. A lot of our competitors are a bit sorry about that. We put them into our own systems, and then our customers use them to build networks, and you perceive what we do as things like mobile access, residential broadband, and data center interconnect. We provide the bandwidth, or our customers do, provide the bandwidth that enable those kinds of everyday activities. Well, thank you very much, and I hope that's been useful. Any questions? I'm not quite sure what time we have to finish, but I'm happy to answer any questions if you have them.
So how fast?
Yes. Oh, sorry. Yes, sir.
Have you been teaching children?
No, I haven't actually. You think I should?
Yeah.
Thanks. Yes.
How fast the really light can travel through the fiber?
Yeah, so that's a really good question. Silica has that fundamental limit because the refractive index of about 1.5-ish. Recently, subsea cables. So I don't know if you remember when I told you about the structure of fiber. We dope the core with germanium to raise the refractive index of the core. Raising the refractive index slows the light down, only by about 1%. But for organizations that have transatlantic cables where you're trying to connect finance centers between, say, London and New York, where they're doing algorithmic trading, which you're trying to shave milliseconds away from the transit path. First of all, they lay the cables over very direct routes, and that's difficult in the Atlantic Ocean because the biggest cause of cable breaks is fishing boats dragging their fishing nets and pulling the cable. It doesn't normally physically break the cable, but it damages the fiber inside. So you've got to be really careful about the fiber routes. But what people are doing, instead of having a core that you dope with germanium and raise the refractive index, you keep the core pure silica and you dope the cladding to reduce the refractive index. So there are various exotic fluorides and various other chemicals you can dope the outer layer. But at the end of the day, you could only ever get to the refractive index of pure silica unless you change the kind of fiber completely. And so now there are people talking about hollow core fiber where you're transmitting through free space or through nitrogen, basically. So that's another option. I think I might have to finish.
Your prediction on 5 years, what is in lab, what is in commercial world?
Oh, what's in the lab today? So there's a show called ECOG, which is happening in Gothenburg in a couple of weeks' time. I wish I could tell you what we're going to announce there, but I'm not allowed to because it's actually a post-deadline paper that we're producing. But what I can tell you is it's a very, very high data rate single wavelength transmission. Because the thing that limits single wavelength transmission is the electronics, it's not the optics. And so we've been pushing some boundaries on the electronics. But yeah, I mean, keep an eye out for that because that will represent the fastest single wavelength transmission reported so far. I think I might have to finish here, but again, thank you very much for your attention.